Now we're going to demonstrate how to do a logistic regression using the R programming language. So for this, we're going to need a data set that has a binary target. And for this, we're going to revisit our friend, the IRIS data set. So for this, I'm going to eventually make a rock curve. So I'm going to have to load in that library. Okay. And now I'm going to take our friend the iris data set and copy it into another variable. I like to work with a variable df for data frame. You could really do anything you want. This is just my convention that actually a lot of people will use df for a generic data frame. Now I'm going to need to create a binary target. So if I just quickly, let's just do df here. You can see this is our iris data set. There's 150 of them, and there's setosas, versicolors, and virginicas. So we're going to need to create a binary target. So this command right here will return a true or a false. So if I say data frame species equal to virginica, that's either going to be true or false, because there could be a setosa or versicolor. So let's just run this thing real fast, just like this. Now we're not going to add that +0 quite yet. Let's just show you what we get here. So if I do this and I look at f, that's our variable, I have 150 values of true and false. Well, I would prefer those to be a number instead of true or false. So if I add 0 to those, R is going to say, oh, he must want these to be numbers instead of trues and falses. So I'm going to do that. And now, look at that. They're all ones and zeros, and that's what we want. Now I'm going to copy this letter F into my data frame. So data frame, and I'm going to call it target. I could call it anything I want, but I'm going to call it target, and I'm going to set it equal to F. So now if I type data frame, look at this. I've got 150 records, but now I've got a new column called target. And you can see that it's always going to be 0 until I get to virginicas. Then they're all ones. Okay, now I don't need that species anymore. Let's get rid of that. So data frame species equals null. It's going to get rid of our data frame. So if I do data frame now, look, it's gone. And all I have is numbers, zeros and ones. And then I got the information on the petals and the sepals. Okay, now how do I do a generalized linear model? Easiest thing in the world. All I need is to do the command glm, generalized linear model, target equals dot, that's all of the records, all the variables. I have to say family equals binomial, and that's it. Data equals data frame. So let's do that real fast. Oops. Okay, now you'll notice that when I did that, I got a warning message. It's not an error, it's a warning, and R is just saying, hey, listen, some of your numbers got really high and I rounded them to 1, or some of them got really low and I rounded them to 0. Not a problem, it's just this is R's way of saying, hey, listen, I rounded things and they, to zeros and 1. And if we do a summary of this, we can see what our coefficients are. And there they are. So you can see, and this is the coefficients that it will give us the logistic or the logit value, not the probability, but the logit. So now how do we do a prediction? Well, it's really easy. We just do P equals predict, give it the name of the model. Right there is M. We're going to send it in the data frame, and we have to say type equals response. And then R is going to be smart enough to say, okay, he wants me to convert that into probability scores. If you don't put that response there, it's going to give you the logit value. You don't want that. You want the probability. So this is the command. Now, if I type P, these guys are all probabilities, but they're kind of hard to read. So I'm going to round those guys to 3 decimal places. And there they go. Look at that. So they're all 3 decimal places long. And you look, this is the ones that got rounded up to 1. And down here, we got some guys rounded to 0. Okay, now let's just do a rock curve for this. So this is familiar code from before. And you're going to see how this is going to be an amazing rock curve here, because this is a really simple problem. And if you look, this is diagonal is random, and this is our model. And look at this. It's nearly perfect. So this is as good as it's going to get. So this is how you do a logistic regression in R. It's a trivial exercise. You just, instead of using linear model, LM, you use GLM, and you have to add this guy here. And when you predict, you have to put this response. That's it. Just for fun, let's see what would happen if we were to do a linear regression. So let's do linear regression on this data, and we're going to put that into M2. So let's do a quick summary of that. And you can see here's our coefficients, but we have an adjusted R squared of 60%. Not bad. I mean, I told you you can get by with using linear regression. It's just not desirable. Let's do a quick prediction on this. So let's put in M2 and data frame, and let's see what we get. So if I do P, look at this. You'll notice that some of my probability scores are actually negative. So there's a negative 19% chance that this thing is going to be a Virginica flower. And over here we have something with 106% chance. So we don't want to do that. So what we will need to do, if you use linear regression, you have to truncate the answers. So what we're going to say is, listen, anybody greater than 100%, we're going to reduce it down to 99.9%. So this is the command that's going to do that. So pmin 999. So let's do that real fast. And you can see now that guy that used to be 106 right there is now down here to 999. Now we still got these negative guys up here that we don't want. So what do we do with them? Well, here's the command for that. Pmax 001. So watch this. If I do P thou, look at that. Nobody is going to be negative now. So they're all going to be less than 1 and more than 0. And let's round these guys to 3 decimal places also. And there they all are. So just for fun, let's take a look at the error distribution for this guy. So this is our prediction. Let's do the target minus P. So let's see what the error distribution is going to look like. Oh, and then we'll plot it. Now remember, we want it to be scattered all over the place, but it's not going to look like that. So you can see we don't have a random distribution of errors. So this is something that's not a desirable thing. Again, as I mentioned, it's not the end of the world if you've got a pattern in your data like this, but if you can use a better type of regression, you should do it. So that's why logistic regression, the fact that logistic regression will never exceed 1 and it will never be less than 0, and it's not going to have this issue with errors. It's just a preferable way to go. But linear regression is a pretty good regression, so you can usually get by using it in most situations. Let's just for fun do the rock curve for this guy, see what that looked like. And you can see it was not as good. I mean, this is still an amazingly good model, but it wasn't as good as the logistic regression. And how about we superimpose both of them on to the same graph and take a quick look. And there you go. You can see the logistic regression, the green line, was really good, and the linear regression was not as good. So in the corporate world, people will often use linear regression if they can get away with it, because it's just so simple to use. But if you're going to start using something in a highly regulated industry, you're going to most likely be required to use logistic regression. So that's why we're going to discuss why it's being used.